Today, I plan to give an idea of exactly why we need pseudodifferential operators. And I'm going to do that through an example, or through a problem rather. So first, define, as we always do, a constant coefficient linear differential operator, like this, of order m. So we'll have the multi-indices, the order of the multi-index being less than m. Here we'll have a complex value, and here's the derivative. So this is our operator. So this is a linear partial differential operator of order m, constant coefficients. And now we define a PDE like this. So we apply this on some distribution u and say it's equal to a distribution f. So suppose f is given and so is p. We want to find u. So solve for u. This is our problem. How would we go about doing this? Well, we know it's a linear differential equation with constant coefficients. So what comes to mind is maybe one of the first things that people learn in an undergraduate course in PDE, which is that method with the Fourier series. So one idea would be just to solve an eigenvalue problem and then use Fourier series. And that's more of an approach for like the Dirichlet problems, boundary value problems, initial value problems, but not for just solving the PDE. And also this PDE is not necessarily of second order. This is of order m, as we can see here. So that won't work. Okay, so the second thing we might think of is, well, we know by the Lagrange-Ehrenpreis theorem, that this has a solution. It is a constant coefficient linear differential operator, and so it must be locally solvable. Okay, so we know it is solvable, but that doesn't actually give us u. So third thing we might think of is, well, we know that if we have a fundamental solution, we might know what a fundamental solution is. Let's say a fundamental solution E, then P of E, so if P of E is equal to delta, then we call E a fundamental solution. This is a fundamental solution. And the fundamental solution is interesting because if we can find one, we know that P is locally solvable, and we can actually determine what the solution is. So the solution will actually be E convolved with F. So if we apply P on E convolution F, that will give us F again. So this operator here, convolution with E, with the fundamental solution, is actually inverse of P. Okay, so we know that a fundamental solution solves the problem. This looks promising, but we don't know how to find the fundamental solution. We know we need a fundamental solution, but how do we obtain E? So what we can do now is, well, we know how to apply the Fourier transform. That's really the major tool in this line of study. So let's just apply the Fourier transform and see what happens. So applying the Fourier transform on both sides, remember we're looking to get a fundamental solution for P. Actually, we should also, sorry, I should have specified earlier, this P is actually also elliptic. And what I mean by elliptic is that its principal symbol, Pm of xi, I think I defined that earlier in one of the previous videos. This is non-zero for every xi in the punctured plane. This is what it means to be elliptic. If we have a variable coefficient linear differential operator, then it just means that this holds for every fixed x. So if we had p xd or something, then this is elliptic if we fix an x and this holds. Okay, so we're considering that P is an elliptic operator. Now the property that matters to us in elliptic operators is that elliptic operators, so maybe I can write that, yes, okay, so the roots of the characteristic polynomial of P are contained in a compact set. Or rather, they are a compact set. Okay, so this is the property that we're going to be using. And so now back to our objective, which is finding explicitly a fundamental solution for P. So we apply the Fourier transform on both sides, which is the most natural thing to do at the moment, if we know what the Fourier transform is. Apply the Fourier transform here and here. And that will give us the characteristic polynomial of P on one side times the Fourier transform of U. And we have something like this. Now, we can divide both sides by this characteristic polynomial here. We'll have something like this. And from here, we want to solve for U, right? So we can take the inverse Fourier transform now. So we take the inverse Fourier transform of both of these guys. And then we'll get U of x equals 1 over 2 pi n, where n is the dimension of the domain, integral over Rn e to the I xi. My handwriting is terrible. I don't know how to draw xi. So this is xi inner product with x times f hat of xi divided by the characteristic polynomial d xi. Okay, so great. Now the problem with this expression here is that it doesn't necessarily make sense. So in general, right? In general, this polynomial might have roots in the integration domain, and so this integrand might explode and it might not be integrable. So this is a problem, and so immediately the first thing that we can think of is to try to get rid of those zeros somehow. And the easiest way, again, through the theory of distribution, something that we're used to, is multiplying by cutoff functions. So we could say, so suppose this is, suppose we have Rn here. This is Rn. And suppose these are the roots of the characteristic polynomial. We know they're contained in some compact set here. So we can take a ball, an open ball that contains this compact set, and define a cutoff function chi, such that chi is 0. Chi is 0 in this ball. We can take another open ball slightly larger than this one to allow chi to grow to 1. And then we say that outside of this slightly larger ball, chi is 1. So this will be our cutoff function that eliminates the zeros of P. So now we can multiply this expression here by xi. So we can introduce a xi right here. Chi of xi. Chi of xi in this integral. And of course, this new integral now won't be, we don't expect this integral here to actually be a solution to P u equals f, because we've just destroyed some information on P. Right, this chi, it did erase the roots of P, but in doing so, it just destroyed any information we have about P in this region here. Right, so we don't expect it to solve that equation anymore. So just for psychological reasons, we'll start to call this uv. We'll call it v of x. Okay, so now we have this experiment. Let's just keep working with it and see where this leads us. So let's rewrite that down here. So we have v of x, which is, I guess, somewhat of an approximate solution. It's the best we have, is equal to this expression here. Okay, so what can we turn this into? Now this just becomes a game of manipulating these symbols and seeing where we can end up. So, well, one thing we haven't done, we've gotten this thing that looks like an approximate solution, but we haven't applied P yet to it and see what it actually gives on the right-hand side, right? So if this were a solution, PD of V would equal F. So let's just see, right? We suspect it's not a solution, but we don't know for sure until we apply P. So let's go ahead and apply P and see what happens. So if we were to apply P on V, how would we evaluate this? We could, so one strategy is to take the Fourier transform of all this, and then we'll take the inverse Fourier transform later. So take the Fourier transform, and that will be P psi of this. Okay, and we know what this is because it's just the Fourier transform of this. And the Fourier transform of that, well, this is just the inverse Fourier transform of this. So this is just a big chain of Fourier transforms and inverse Fourier transforms. So let me see if I can write this as simply as possible. So this guy here is equal to just that above part without the integral. I have this. Okay, and then we want to take, so now we have this guy cancel with this, so now this entire right hand side here is equal to just this. Okay, perfect. So now we want to take the inverse Fourier transform, right? So we can get on the left hand side PD of V. And so if we take the inverse Fourier transform of this, we have 1 over 2 pi n ei psi x d xi. Okay, so this is the expression we end up with. And we can still manipulate this further. So let's try to get an f to appear in here. So we can just use an old teacher of mine used to call this the dirty analysis trick, which is summing and subtracting the thing you want to appear. We want an f to appear on the right-hand side. So what we can do is just sum f and subtract f. Now we can rewrite f to look more similar to this term on the right-hand side by introducing Fourier transforms. So in this case, when I say sum and subtract f, I mean sum and subtract the inverse Fourier transform of the Fourier transform of f. That's what I mean. So you can get the integrals in there. So I won't write this. This is going to be a medium-sized expression, but you can see how things would cancel out, or not cancel out, but rather redistribute themselves, so that you get that this PD, I should rewrite that PD of V would be f of x. F of x minus 1 over 2 pi n this here, and here we go. So this is what we get. So we have an f here. This is what we wanted in the beginning. We wanted v to solve p, but we have this term here. This is our error term, and we can actually rewrite this error term as r f. So it's some operator r applied on f. We call r a regularizing operator, and we call it a regularizing operator because this here, 1 minus our cutoff function, is actually now 1. So this is actually 1 in this smaller ball. Remember that ball that chi is 0 on, and it's 0 outside that larger ball. So this is kind of like a new cutoff function, and clearly this new cutoff function is in C infinity C. It's a smooth function of compact support, meaning it is the Fourier transform. It's the Fourier transform of a C infinity function. So 1 minus chi is the Fourier transform of a C infinity function by the Paley-Wiener theorem. Paley-Wiener theorem. So what does this mean? I'm just going to erase this part here then. So that means that we can rewrite this as, let's say, we can call h. So h is that function that smooth function whose Fourier transform is 1 minus chi. So we can call this the Fourier transform of h of psi. And now by that property so we have a property that Fourier transform takes multiplications to convolutions. So this integrand here, except that e to the I psi x actually equals the Fourier transform of the convolution of f with h. And what we have involving this whole expression is, of course, the inverse Fourier transform. So this entire r fx is nothing more than f convolution with h, which is a C infinity function. Therefore, by properties of the convolution, this must also be C infinity. And so that's why this R is called a regularizing operator. Regularizing operator. Because f can be any distribution you want, as long as it's compact support, of course, so that convolution is defined. That f convolution with h will return always a smooth function, independent of the regularity of f. So we have this then. Okay, so our error is a regularizing operator on f. Okay. What else? What else can we say? So we've written this regularizing operator as a convolution with this h, which is a smooth function. We can actually do something similar with this guy over here. So with this guy over here, note that we have, I should probably copy and paste this down here. Or not. Yeah, I'll just write in blue. So we have this guy up here. And I'll note that chi, so chi is the cutoff function that equals 1 outside of the larger ball. And here we have the inverse of a polynomial. Is that right? Yes. Okay. So that means that this term over here, which is, let's see, p to the minus 1 times chi, is going to look something like, let me do the graph down here. This is p minus 1 chi. So this is going to be 0, of course, within the smaller ball because of chi. And then as soon as chi actually is 1, so let's say it's 1 outside of here, here is something happens, whatever, it's bounded. And then outside of this, we have this polynomial decay. So that's what this looks like. We have something like this, actually. Something like this. And so this, because of the polynomial decay and it's bounded and everything, this actually is a tempered distribution. So it's a function, but it's also a tempered distribution. So this is a tempered distribution, meaning, again, that we can find an inverse Fourier transform of it that is also a tempered distribution. So there exists, let's say, a k such that, so there's the k, which is a tempered distribution also, such that the Fourier transform of k is p minus 1 chi. And by the same argument that we used here, right, to obtain a characterization of the regularizing operator by a convolution operator, we can also say that that v, let me think about this for a second. Yeah, that v, okay. So we have this v equals this whole integral over here. And so then we can rewrite this as v equals the convolution of k, which is this guy over here, with the convolution of k with f. Okay, that should be right because there's an f here. Yeah, so by that same property of the Fourier transform that it transforms multiplications into convolutions, we have the same thing going on here. This time this isn't a regularizing operator because this isn't necessarily smooth. This is just a tempered distribution, K. Okay, so we've expressed V as this convolution, and we have expressed RF. Is that correct? Yes, RF as this convolution. Let's do HF. Okay. So now we are in a position to go back to this expression here. Remember, we're still trying to hunt for a fundamental solution of that PDE, right? We got close to finding a solution U, and then we realized we had to adjust for the roots of P, and then we ended up with a V that doesn't exactly solve our PDE because of this error term RF. But now let's see what we get. So we've manipulated some terms, and we've actually characterized V by a convolution. We've characterized R by a convolution. So let's try to substitute this back into the main equation that we have, which is the one for the PDE up here. So let's substitute these back there. And let's actually also, since we're searching for a fundamental solution, let's just write F as, let's take F to be the Dirac delta. Okay, so this equation here would turn directly into P of V is K convolution F, but F is the Dirac delta, so this would just be PdK, which would equal, so originally we had F minus RF on the right hand side, and since F is the Dirac delta, here we have the delta, and here is R times R, the regularizing operator of the Dirac delta, which is, so this regularizing operator, of course, is H delta, and that's just H. So here we have it. We have this new identity here. Stating that we truly almost got a fundamental solution because, right, all we needed is this, but we have this error H now, but H is a smooth function. H is a smooth function. So modulo smooth functions, we actually got a fundamental solution. Of course, that doesn't solve our problem, but if we arrive actually at an identity like this, by definition, we call K a parametrics of P. And parametrices are important because they help us determine the regularity of a solution. They might not give a solution, but they determine the regularity of a solution. So that's nice. So we know if P is, so if PD is constant coefficient and elliptic, then we can find a parametrics. Not only there exists one, but we can find it. We have just constructed one. Okay. So in fact, well, before I move on to some other observations, I should note that in this case, we can actually obtain a fundamental solution based on the parametrics. So if we've gotten this far, then we can actually solve, we can define a fundamental solution E in this way, and you can check that it's a fundamental solution later. But so we can define E is K, which is our parametrics, plus some W, where W is the solution of PD, W equals H. Right, I think that's it, yeah. Okay, so this is the fundamental solution. And so I said it's always possible, and you might be wondering, well, how is it always possible if, I guess the existence of this W depends on this equation having a solution. But note that in this case, it does have a solution because this right-hand side, H, is an analytic function by the way we defined it using the Paley-Wiener theorem. So this is analytic. And this is constant coefficient. This is constant coefficient. In other words, analytic coefficients in particular. So by the Cauchy-Kovalevskaya theorem, this is actually solvable. So just apply the Cauchy-Kovalevskaya theorem, and we have a W, and therefore we have a fundamental solution always in this case. So yeah, this is a nice theorem. For elliptic constant coefficient differential operators, we always have a solution. We can always actually build a fundamental solution. We knew that it did, in fact, always have a solution because of the Magron-Jervin-Price theorem. But now we can actually construct a fundamental solution. This is nice. And so we've accomplished what we set out to do. So technically, the problem stops here. We have solved it. But I still haven't said what this has to do with pseudo-differential operators. And so the thing is that, so it's been known since the 50s, actually, this whole technique about determining parametrices. And we actually also know that it can be applied, so this can be applied basically in the same way with some slight difficulties, some slight extra difficulties in the variable coefficient case. This can be applied in the variable coefficient case. So that is for P of xt. And we can obtain our parametric. Oh, yes, of course, this has to be elliptic also. So in this case, we can obtain a parametrics much in the same way that we just did. And then we would arrive at, let's see here, which one of these equations do I want? Yeah, probably PD, yeah. No, it's actually the V. Okay, so this operator here is, so we arrive at something similar to this in the variable coefficient case. Let me just see if I can copy this down here. You have V of x, you have 1 over 2 pi. You have f hat. I think this is what we had, right? Yes. And so we arrive at something similar to this with some extra x's in here probably. So we have maybe an x in this argument. And, but these are just details. We arrive at something similar to this, and we would like to actually generate, so we know that V, right? We got that V was some k convolution with f, I believe. K convolution with f. And this k convolution here, this is the operator that we want to generalize. So this would be kind of the approximate inverse to P, right? And so we actually, sorry, I didn't state the goal of pseudodifferential operators. The goal of pseudodifferential operators is that we can always invert, in a sense, the elliptic operators. So if you have an elliptic differential operator, it can be variable coefficient if you want. We would like to find an extension of the space of linear partial differential operators. So we have these guys here. We'd like to extend it. We'd like to extend it such that we can always invert the elliptic operators in a sense. And the sense that we're talking about is finding a parametrics. Now, in the context of this space here, it's strange because inverting actually, it's not inverting in a sense, it's literally inverting. This space is taken modulo regularizing operators, so it just forgets that error term. And so parametrices in this space are actually inverses. They're actually solutions of the PDE. So we want to find a space in which this is always in that space. This k star here. So that's the motivation. And so we can look, the way you construct it is you look at this right-hand side, and we want to generalize this right-hand side. We can notice that on this right-hand side, it just looks like it just looks like there's an E, there's an F hat, and there's something multiplying this F hat. We can call this something here. Let's call this something A of x psi. This A of x psi is the part that we generalize. We say this A of x psi now, instead of being limited to be only a cutoff function times the inverse of a polynomial, we now say that this can be anything smooth, that is, anything in C infinity, that satisfies a bound that this particular case also satisfies. And that bound is, I'm just going to say the bound approximately. That bound is that the derivatives of A have to grow on the order of, they have to grow in polynomial fashion on the order of psi to the m minus alpha, I believe. So something like this. So if this A, which we call a symbol, so this is the symbol of the pseudodifferential operator. It's the pseudodifferential operator is defined by symbol. The symbol must be a C infinity function that satisfies some bound on its derivatives. And so this is how we generalize. Then we take this right-hand side with an arbitrary symbol, and this would define an operator of this type here. And we'd call the operators of this kind pseudodifferential operators. Actually, we call them standard pseudodifferential operators. And it's in this class that you can always invert elliptic operators. Now, so this is the motivation for pseudodifferential operators, and this is approximately how they're defined. But there's also another problem, right? We know that parametrices help to determine the regularity of solutions, and by regularity of solutions, of course, I mean hyperellipticity of the operator. So parametrics, which is an inverse in pseudodifferential operators. Is the same thing as determining the hyperellipticity of P. So, but we can only do this. The space of pseudodifferential operators is only guaranteed to invert elliptic operators. But we have this property here, so it would be natural to want to extend this space further, such that we can also always invert hypoelliptic operators. And in fact, this has also been done. And if we call this intermediate space the standard pseudodifferential operators, we can extend it further to what's called the rho delta pseudodifferential operators, where a rho and a delta are specified. And so in this class here, we can invert hypoelliptic operators. Which gives us a nice way to determine the hypoellipticity of an operator. But yeah, so that's the motivation that I had to give today. The pseudodifferential operators, they are actually, this is the motivation, and it is actually the place where they were historically born. So there's this technique that exists since the 50s of trying to find the fundamental solution of elliptic operators. And it was out of this curiosity of if there's a larger space other than the linear partial differential operators where we can always find a parametrics of an elliptic operator, that pseudodifferential operators were born. And yeah, so that's the motivation. In the next video, I might define pseudodifferential operators more rigorously, or maybe start talking about their interesting properties.